Now that we understand how to find a matrix vector product, where we multiply a matrix by a vector or multiply a vector by a matrix, we have the foundational knowledge we need to start talking about the 4 fundamental subspaces of linear algebra, the first of which is going to be what's called the null space. In just a few lessons, we're going to talk about the column space, and then later on in the course, the other 2 of the 4 fundamental subspaces. But the first one we're going to talk about is the null space. So first of all, when we say the null space, the fact that we use the word space here is intentional, and that's because the null space specifically is a subspace. So the null space is a subspace. And remember that in order to be a subspace, we have to meet 3 criteria. First of all, the space needs to include the 0 vector. So before we show that the null space includes the 0 vector, let's talk about what the null space is. The null space, looking at this equation here, the matrix A times the vector x is equal to the 0 vector. This equation is what defines the null space. So any vector x that satisfies the equation A times the vector x equals 0, that vector x is in the null space. And specifically, it's in the null space of A, and we write the null space of A as n of A, the null space of A. If we were dealing with the matrix B, then we would have n of B. If we were dealing with the matrix C, we would have n of C. But the idea is that if you have a matrix A that we've been given in this equation here, any vector x, it doesn't matter what that vector is, any vector x that you can multiply A by and get the 0 vector, that x is going to be in the null space. And the null space is the collection, it's the subspace that includes all of the vectors x that will satisfy this equation. Sometimes the null space is just going to include nothing but the 0 vector, and then other times it'll include the 0 vector and other vectors in addition to that. And whether or not the null space includes just the 0 vector or the 0 vector plus some other vectors is going to tell us more about the matrix A, and we'll talk about that in a second. So all the vectors x that satisfy A times x equals 0 are the set of vectors that make up the null space of the matrix A. So with that in mind, that is the null space of a particular matrix, let's show that the null space will always include the 0 vector. So if the 0 vector is included in the null space, then that means that we're saying that this vector x right here is the 0 vector, or if I plug the 0 vector in for x, it's going to satisfy this equation. And of course we can see that that's true, because if we have some matrix A, and let's just use a 2 by 2 matrix, let's say we have A 1 1, here we have A 1 2, we have A 2 1, and we have A 2 2, and it doesn't matter what the matrix dimensions are, but let's start here with a 2 by 2. If we multiply that by the 0 vector, in other words, we're plugging the 0 vector in for the vector x right here, of course, the result of that is going to be a 2 by 1 matrix. We're going to get A 1 1 times 0 plus A 1 2 times 0. We're going to get A 2 1 times 0 plus A 2 2 times 0 when we take dot products. And we can see that the result will be across the top row 0 plus 0, which is 0, and across the bottom row 0 plus 0, which is 0. And no matter how big or small this matrix A becomes, and regardless of the dimensions of this column vector x, so this is A, this is x, as long as x is the 0 vector, we're always going to end up over here with the 0 vector. So the 0 vector can always be plugged in for the vector x, which means the 0 vector is always going to satisfy this equation. It's always going to be a vector x, which is a member of the null space. So the 0 vector will always be included in the null space. The second condition that we need to meet in order for something to be considered a subspace is that it needs to be closed under addition. And we can show that that's the case because if we say that we have a vector x1 that's in the null space and a vector x2 that's in the null space, then we know that both of these satisfy this equation. So we know that ax sub 1 is going to be equal to the 0 vector, and we know that ax sub 2 will be equal to the 0 vector, because if x sub 1 and x sub 2 are in the null space, they satisfy this equation, which means we need to be able to plug them in for the vector x. So we can plug them in for the vector x sub 1 and x sub 2 are both in the null space. So now the question is the vector x sub 1 plus x sub 2 in the null space? That's what it means to be closed under addition. Well, if we just add these two equations together, which is a perfectly valid operation to do, we can always add two equations together. On the left-hand side over here, we get a x sub 1 plus a x sub 2, and on the right-hand side, we get the 0 vector plus the 0 vector. Well, adding two 0 vectors together is always still just going to be the 0 vector, so the right-hand side is still 0. And then we know from properties of matrix multiplication that matrix multiplication is distributive. So this is the same here as saying a times x1 plus x2. We're able to factor out the matrix A without changing the value at all. But notice here that this equation now is the same as this equation up here, a times the vector x equals 0. We're saying that the vector x1 plus the vector x2, that vector, which is the sum of those two, satisfies this equation, a times the vector x equals 0. So I'm saying if the vector x1 and the vector x2 are both in the null space, then I can prove here that the vector x1 plus the vector x2, that sum vector, is also in the null space, and so I know that the null space is closed under addition. And then the last thing we need to show that the null space is a subspace is that it's closed under scalar multiplication. And we'll again go back to properties of matrices. If we're saying that the null space is closed under scalar multiplication, if I again say that I pick a vector x sub 1, and I'm going to say that that is in the null space, it's a member of the null space, then I have to show that c times the vector x sub 1 is also going to be in the null space, that this vector is also in the null space. Well, if I plug this vector into this equation that defines the null space, if I say a times c times the vector x1 is equal to the 0 vector, I know from properties of matrix multiplication that I can pull this scalar c out in front. So I can rewrite this as c times a x1 is equal to the 0 vector. Well, I already know that a times the vector x1 is equal to the 0 vector because I said over here that x sub 1 was a member of the null space. So I already know this equation right here to be true because x sub 1 is in the null space. So I'm saying that a times the vector x sub 1 is equal to the 0 vector, which means I can replace down here a times x sub 1 with the 0 vector, and I get c times the 0 vector is equal to the 0 vector. Well, when I multiply a scalar c by the 0 vector, I still just get the 0 vector. And so because I end up with a true equation here, I can say that the null space is closed under scalar multiplication. And because I meet these three criteria, I know that the null space is a subspace. And that's always going to be the case. We proved that with all of these generic vectors here. So no matter which vector I pick for x sub 1 or x sub 2, these things are always going to hold. The null space is a subspace. So let's do a simple example where we find a vector that's in the null space. Let's say we're given the matrix A, and it's a 2 by 2 matrix 4, -2, 2, -1, and we want to find vectors that are in the null space of A. Well, in order to do that, we can simply plug this matrix into the null space equation here. So we can say, instead of A, we'll say 4, -2, 2, -1, and we'll multiply that by a vector x. So instead of just saying the vector x here, we'll break it apart into its components, x1 and x2, and we'll set that equal to the 0 vector. And now we want to solve this for values of x sub 1 and x sub 2 that make this equation true. Well, we have two options for going about that. We could break this apart into a system of equations. This would be the old way to do it. We would break it apart into a system of equations, and we would say 4x sub 1 minus 2x sub 2 equals 0. We're taking here the dot product of the first row with this column vector. So we say 4 times x sub 1 plus a negative 2 times x sub 2 is equal to this top 0 here. And then we would go across the bottom. We'd take the dot product of 2, negative 1, and the column vector set equal to the 0 vector on the bottom, and we would say 2x sub 1 minus 1 times x sub 2 is equal to 0. Now we've got a system of two equations in terms of two unknowns, and we could solve this system using substitution, elimination, or graphing for values of x sub 1 and x sub 2. Or we could do it the new way, which is the matrix way, where we set up an augmented matrix. We say 4, negative 2, 2, negative 1, and we augment that with the solution, which is the 0 vector, and then we get this into reduced row echelon form. So in order to do that, we could start by dividing through the first row by 4, or multiplying through the first row by 1/4. But notice that this second row here is exactly half of the first row already. So let's actually skip one step ahead and replace the second row with the first row minus 2 times the second row. So we'll replace the second row with the first row minus 2 times the second row. That'll help us zero out the 2 right here and make our math a little bit easier. So we will here replace the second row with 4 minus 2 times 2, or 4 minus 4 is 0. Negative 2 minus 2 times a negative 1 is a negative 2 plus 2, or 0. And then 0 minus 2 times 0 is 0 minus 0, or 0. And then for the first row, we could leave it the same, 4, negative 2, and 0. Now let's go ahead and find the pivot entry in that first row where we divide through by 4. So dividing through by 4 gives us 1, gives us a negative 1/2, and gives us a 0. And then we're left with zeros all across the bottom. And our matrix is now in reduced row echelon form. We have our full row of zeros at the bottom. We have our pivot entry of 1. So what this is telling us here, remember that these columns are associated with values of x sub 1 and x sub 2. So if we break this apart into a system of equations, the second row tells us nothing. We have 0 times x sub 1 plus 0 times x sub 2 is equal to 0. We just have 0 equals 0. We get nothing from that. But from the first row, we can rewrite that as 1 times x sub 1, or x sub 1, minus 1/2 times x sub 2, so minus 1/2 x sub 2, is equal to 0. If we add 1/2 x sub 2 to both sides, we get x sub 1 is equal to 1/2 x sub 2. What this is telling me here is that any pair of values, x sub 1 and x sub 2, that satisfy this equation are going to be included in the null space of A. So with that in mind, let's first think about the 0 vector. We said that the 0 vector will always be included in the null space. And in fact, if we look at this here, if we plug in 0 for x sub 1, we're going to get 0 for x sub 2. So we can see that the 0 vector is in fact included in the null space. And I could find an infinite number of other vectors that are included in the null space. If I pick 1 for x sub 1, I would multiply both sides by 2, and I would get x sub 2 equals 2. If I pick 2 for x sub 1, I get 2 over here. I multiply both sides by 2 to get 4. I get x sub 2 equals 4. And you can see the pattern here. If I pick 3 for x sub 1, I'm going to get 6 for x sub 2. All of these vectors are included in the null space. Or I could go the other way. I could pick a couple values for x sub 2. Let's say we pick 1 for x sub 2. Then x sub 1 is going to be 1/2. If I pick 2 for x sub 2, I can see that x sub 1 is going to be 1/2 times 2 is 1. And so I get the vector 1, 2. That's the one I found earlier here when we plugged in 1 for x sub 1. But the point is that I could keep going, picking any values that I want to for x sub 1 to find associated values for x sub 2, or vice versa, and I'd get an infinite number of vectors here in the null space. Now here's the interesting thing about the null space. The vectors that are in the null space tell us about the linear dependence or linear independence of the columns in the matrix A. So I'm saying here that this is the null space of A. It's all of these vectors. We'll put a ... to indicate that there are infinitely more. But the null space of A is any vector that satisfies this equation here that relates x sub 1 and x sub 2. What we want to realize is that if the null space includes only the zero vector is the only vector in the null space, there are no other vectors in the null space. If that's the case, then that tells us that the column vectors of matrix A are linearly independent. And the reason for that is because another way to write this matrix equation is to take the first column vector of A, 4, 2, multiplied by this x1 value. So we could rewrite this as x sub 1 times the column vector 4, 2 plus x sub 2 times the second column vector negative 2, negative 1 set equal to the zero vector. This equation means the same thing as this equation down here, and this should look familiar to us. This was the test for linear independence that we talked about earlier. We said that if we set up a linear combination of vectors and we set that equal to the zero vector, we called x sub 1 c sub 1, and we called x sub 2 c sub 2, and we said if the only combination of c sub 1 and c sub 2 that makes this equation true are 0 and 0, in other words, if all those c sub 1, c sub 2 values are 0 and only 0, that's the only solution to this equation, then these vectors are linearly independent. But if we could find some other combination of c sub 1 and c sub 2, or in this case, x sub 1 and x sub 2, that make this equation true, then these vectors, 4, 2 and negative 2, 1, are linearly dependent. And we're saying exactly the same thing here with the null space. We found this other combination here where there are other values of x1 and x sub 2 that satisfy this equation. For instance, if I take the vector 1, 2, where x sub 1 is 1 and x sub 2 is 2, I'm saying up here in this equation, take 1 of the vector 4, 2, and 2 of the vector negative 2, negative 1, take their combination, and you'll get the zero vector. Or if I use the vector 2, 4 down here, take 2 of this vector and 4 of this vector, put them together, and you'll get the zero vector. So there are other linear combinations of these vectors that give me the zero vector other than just the zero vector itself, which tells you that these column vectors of A are linearly dependent. But if the null space of A includes only the zero vector, so I can only find the zero vector, that means up here in my linear combination, the only possible solution is x sub 1 equals 0 and x sub 2 equals 0, or the way we talked about it before, c sub 1 equals 0 and c sub 2 equals 0. 0, 0 is the only combination that works, in which case I know that these vectors are linearly independent. So the conclusion that we're coming to is we're saying that if the null space of A is only the zero vector, then my conclusion is that the column vectors of A are linearly independent. But if the null space of A includes the zero vector, as well as any other vector, we'll call it x sub 1, x sub 2, then I know that the column vectors of A are linearly dependent. And the opposite is also true. If I look at A, before we've even talked about the null space, if I can look at A and see that its column vectors are linearly independent, then I know that the null space will only include the zero vector. But if I look at the column vectors of A and I can conclude that they are linearly dependent, then I know that the null space of A is going to include the zero vector, but also at least one other vector. There's going to be at least one other vector in the null space of A. And I can see that here just by looking at the column vectors of A. I can see here that I have the vector 4, 2 and the vector negative 2, negative 1. Well, if I take the second vector here, negative 2, negative 1, and I multiply it by a scalar of negative 2, negative 2 times a negative 2 gives me 4 right here, and negative 2 times a negative 1 gives me a positive 2 right here. So multiplying the second column vector by a scalar of negative 2 gives me this first column vector 4, 2, and because these are related by just a scalar, that means they're scalar multiples of each other, which means these column vectors are linearly dependent. They're collinear or parallel. they're linearly dependent. So right away, before I even try to find or define the null space, I might notice that the column vectors of A are linearly dependent, and therefore when I'm trying to find the vectors that are included in the null space, I know that I'm going to get the 0 vector, of course, always, but I know that I'm also looking for other vectors that are guaranteed to be in the null space because the column vectors of A are linearly dependent.